Good morning students, 12th standard physics. So in this class we are going to discuss about Faraday's law of electromagnetic induction. So whenever a magnetic flux linked with a closed coil changes, an EMF induced, hence electric current flows in the circuit. So whenever a magnetic flux linked with a closed coil changes. So from the first experiment, that is a coil is connected with a galvanometer, say a bar magnet. So bar magnet, so around the bar magnet there is a magnetic field starts from north and end at south. So we are pushing the magnet towards the coil. So there is a change in magnetic flux linked with the coil. So there is an induced EMF produced in the coil that is sensed through the galvanometer. So this is the first experiment. Now I am going to move away from the coil. So the bar magnet is moved away from the magnet, that is away from the coil. So again there is a change. So again there is a change in magnetic flux linked with the coil. Again there is a deflection. Now I am placing the magnet just inside the coil, but there is no deflection in the galvanometer. So there is a production of current, that is induced EMF is sensed using the galvanometer. Then experiment number 2. So again a coil is connected to the battery and a key. So key is closed at the first condition. So key is closed means the current flows inside the coil. So current carrying loop acts as a bar magnet, so already we know. So the bar magnet means, so one end of the coil may be a north, so another end may be a south pole. So there is a magnetic flux. So magnetic flux means the magnetic field lines. So number of field lines crossing through the given area is magnetic flux. So if current, that is if we close the circuit, that means the key is closed, so current increase from 0 to maximum. So there is a change in magnetic flux. So the current is increased. So current I is directly proportional to magnetic field. So if current increase means magnetic field increases. So again magnetic flux, that is the number of field line increases. So there is a change in magnetic flux linked with the coil changes. There is an induced EMF produced in the secondary coil. So that is sensed through the galvanometer. Again I am open the circuit. So open the circuit just, so there is a degrees of current from maximum to 0. So again there is a change in magnetic flux linked with the coil. So again there is a deflection. Now the current reaches from 0 to maximum, reaches a steady state, so there is no deflection. The current decreases from maximum to 0. At 0 state there is no deflection. So there is a change in magnetic flux linked with the coil and EMF is induced in the coil. So that is electromagnetic induction. Then Faraday's first law, again the same. So whenever the magnetic flux linked with the closed circuit changes, an EMF induced in the circuit which lasts in the circuit as long as the magnetic flux is changing. So how long the magnetic flux changes, it depends upon the induced EMF. So how much induced EMF we get is how long the magnetic flux is changes. Then second law, so what is the magnitude of induced EMF? So it's a value. So it is in a closed circuit is equal to time rate, again that how long, that is time rate of change of magnetic flux linked with the circuit. So it is increasing from 0 to maximum at how long, maybe a 0.5 second or 0.2 seconds. So there is a change in magnetic flux. So there is a change in, there is a current flow in, that is induced EMF in the circuit, that is induced EMF in the coil. So there is a deflection in the galvanometer. So that is as long as the magnetic flux is changing. So the value is time rate of change of magnetic flux linked with the circuit. Then so the induced EMF epsilon equal to d pi by dt. So there is a change in magnetic flux with respect to time. If it is a single turn, if it is a n number of turns means, so it's n number of turns, so the total induced EMF is equal to n times d pi by dt. So just take an inside, so n pi b, so that is magnetic flux. So that is the flux linkage. So it's a product of number of turns and magnetic flux linked with the coil. Then so I am going to show a problem so related to the induced EMF. So consider a coil have an area 200 centimeter squared, then it is wound 400 number of turns. So it's 40 turns, it's wound on that. There is, it is placed in the magnetic flux density 2 Weber meter power minus 2. So its centimeter should be converted into meter. So 200 into, here centimeter should be 10 power minus 2 square, so 10 power minus 4. Then 200 is converted 2 into 10 power 2, so 10 power plus 2, 10 power minus 2 will get finally 2 into 10 power minus 2 meter square. It's so simple. Then, so what is the question? So initially, so this is a plane, so consider say area 200 centimeter square. So initially it is placed in a uniform magnetic field perpendicular. So initially it is placed in a magnetic field, it's with the field, the plane, this is the plane. So this is a, so we have so many confusions. So this is the direction of magnetic field. So this is the direction of, again, so this is the direction of plane. So what is the angle? So what is the direction of n cap? So same direction. So it's the angle between, it's perpendicular to the magnetic field. The plane is perpendicular to the magnetic field. So the n cap and B are parallel. So theta equal to 0 degree. So the magnetic field lines, maximum number of magnetic field lines crosses. Now the plane is with the field, 30 degree with the field. So the plane makes an angle 30 degree with the field. So makes an angle 30 degree with the field. That means, so what is the angle theta? So theta, that is here n cap goes here, that is normal to the plane. So what is the theta? Theta is the angle between magnetic field and n cap. So it's 30 degree, so it's totally 90 degree. So I want magnetic field and n cap. So it's 90 minus 30, it's 60 degree. So theta equal to 60 degree. So this is the way. So we got that 60 degree from 30 degree. So magnetic flux phi, that is initial magnetic flux. So initially the plane is 30 degree with the magnetic field. Again it rotates and make it final at 90 degree, that is perpendicular to the magnetic field. So what is the induced EMF produced in the plane? So that is magnetic flux Pa cos theta. So theta equal to 60 degree, cos 60 is equal to 1 by 2. So just substitute the values, you will get the answer 2 into 10 power minus 2 Weber. Then, so what is the final magnetic flux? So final magnetic flux, so it is with the field, it's 30 degree with the field, it rotates, again after 0.2 seconds it's come back to, it's 90 degree, it didn't say it's just perpendicular to the magnetic field, they said like that, the plane is perpendicular to the magnetic field. That means theta equal to 0, that is the plane is 30 degree, initially 30 degree, again it rotates and come back to, that is perpendicular to the magnetic field. So theta equal to here, so theta equal to 30 is converted into 60 degree first, then final is 0 degree. So that is angle between n cap and magnetic field is 0. So if it is, the plane is perpendicular to the magnetic field. So cos 0 1, so 2 into 2 4 into 10 power minus 2 Weber. Then, so we are going to find what is the magnetic, that is induced EMF produced in the plane if it is placed in a 2 Weber meter power minus 2 magnetic flux density. So induced EMF is equal to n times d pi by dt. So n number of times, that is 40 times. Then there is a change in magnetic flux from, that is final minus initial, so 4 minus 2 2. Just you can easily get, so multiply and divided by 10. So 0.2 into 10 is 2. Then 10, here 40, it's 400. So 4 into 10 power 2, so 10 power minus 2. So 10 power 2 and 10 power minus 2 cancel. Finally you will get that induced EMF equal to 4 volt. So it's a nice problem. So in this class we have discussed Faraday's law of electromagnetic induction, then first law and second law, then induced EMF n times d pi by dt. So we do a nice problem. So okay students.